Friends, Romans, and countrymen, let's get going with lecture. Okay. Today we're going to finish up. I know you guys are excited. We're going to finish up talking about black holes today and all the mysterious things that begin to unfold at the event horizon. And the idea that I introduced last time was gravitational lensing. We'll take another look at that. And then we'll get down to some stuff. At the end of lecture today, we'll do a review session using iClicker and self-paced polling mode, SPP. And that will be converted into some bonus points. And so we'll be handing out a handout, and you'll click through it like on exams, except now you've got 21 items, and we'll get you started on that at the end of class. Also, final exam Tuesday next week, 1 p.m. Be there or be toast. I'd like to say be there or be square, but question. Is there what? Oh yeah, observatory. Is it green? Is it? I don't know. Could somebody check? It was purple this morning when I checked. So can somebody see quickly if they've gone green? Still purple? Okay. If you want to get to the bonus point activity, you got to hush. Sam. Yeah. Sorry, I have to call you out by name. Keep your eye on the Nights Under the Stars website. If it goes green tonight, go if you can. And even if you've already been a couple times, there'll be more stuff to see. By the way, I got up early this morning and was able, I saw quite a few stars and constellations. Saw the Big Dipper this morning on my way to school. It's 6 a.m., riding the bus. So also, try to do that. We'll also have a special mega review homework inside web courses, like our little teeny homeworks, but this one will be bigger. And I'll convert that one. It'll be a study tool for you. And so at the end of exam week, I'll convert that into bonus points as well. All right? Now remember, if it does go green at the observatory, make sure that you turn in the handout, the observation handout, legible handwriting, not with a highlighter. Use a pencil or a pen. You don't have to be another Rembrandt with your skill, but it does have to be legible. And hand that in to them. Don't bring it to me at the exam. Just give it to those guys. That's what they're supposed to be doing. All right? So they'll have them there. And if you haven't been there, try to get there tonight, hopefully, if the weather cooperates. Final exam is Tuesday, and let me just remind you, it's the middle of the day, 1 p.m., so I'm expecting nobody to come late. Oh, my dog ate my alarm clock or something like that. All right, and I'm not, and you know, the thing is, you guys are laughing, but you would not believe the excuses that people bring up. But if you don't get here before the first person leaves, that's it. You ain't going to take the final. All right, and that might be 1:30. So if you're thinking about coming here on next Tuesday at the class time, 1:30, you're out probably, because there'll be somebody that's already finished. All right, so just get here at 1. Everything will be good. It's double the size of a midterm. So mentally think to yourself, how long do I take for a midterm usually? And just multiply that by 2. And then add on another maybe 10 minutes for extra, review of checking your answers and stuff. But we have almost 3 full hours. So it should be good. Question over here. Observatory? I don't know. But look at what did they say? 6:30 tonight? If it goes green, it'll be 6:30. All right, so hopefully it'll go. Yeah, Kayla.
For the bonus points, do we have to get the questions correct or just answer them?
For today's clicker session, yes, you have to get them correct. All right, so consider it like a homework in that respect. Question.
Speaking of homework, are we having that extra credit homework thing?
Yeah, this weekend I'll get it set up and you'll have it to study with. All right, now. See, because I can hear when you're talking. No, don't look at her. Look at me. Dude, look at me. Cameron, the guy next to you. No, not here. The guy right next to you. Yeah. Hush. You're right in the middle of everybody. You're distracting everybody else. You're distracting me. I can hear everything you're saying. All right? So do the zip zap and let's get going. Good. All right, last time we talked about light cones. Light cones, what they do at the event horizon is what we want to get to and try to tackle today and see how that unfolds at the event horizon of a black hole. Now, we got some work to do before that. A lot of unusual concepts are going to attempt to infiltrate your mind today. Now, I have a clicker question. Go ahead and turn on your clickers. Frequency DD, for those of you that may not be familiar with the clicker procedures, because you're not here a lot. Anyways, clicker question number 1 of many today is this. And it's kind of a mental exercise and also a survey. So give me your best guess, and I'll grade everybody correctly on this one. All right? Give me your best guess. Is it possible to make a map of the entire XY plane? Like a sheet of graph paper, but all the way out to infinity? Infinity to infinity? Can you remap that onto a finite piece of paper? Yes, no, or no way? Go ahead and vote, but think. All right. All 3. Okay. 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. 0. Go ahead and show the students this. Now here's how you guys voted. And the majority of you voted yes, probably because you talked to the guys in the first class. They voted majority no. Now the no votes here are 44%, so that's roughly the flip-flop of the morning class. Go ahead and go back to the podcast. The answer is yes. And yeah, you can do this task. You can map an infinite two-dimensional plane onto a finite piece of paper if your paper is in the shape of a sphere. So here's how you do it. All right, go ahead and make a sketch like this. No, make a plane, okay? Go ahead and sketch in your plane, and then kind of trace in a sphere. And then identify the north pole of your sphere. So up here's the north pole, and down here's the south pole, all right? And so this is one way to do it, all right? So the method is you choose a point on plane S. So this is point S over here. So like, in a card game, pick a card, any card. Just pick a point, any point out on that plane. And then from the North Pole up here, draw a straight line to the point you've chosen. Now, it's going to go underground and poke out of the surface of the sphere somewhere about here. All right, now that's point P. And that is unique. For every point on this plane, there's only one point P on the sphere. Now they're not equally spaced on the sphere. So if it's 2 meters apart on the plane, they might not be 2 meters apart on the sphere. But they'll all be in there. The entire infinite plane. Here's another picture. I think you might like this picture a little bit better. And this one is with the sphere sitting on the plane. This is another variation of this mapping strategy. But it's still the same thing. Pick a point out here, this red point, Z, in this sketch, and draw a line from it up to the North Pole. That's the blue point up here. And where it pokes through the surface of your sphere, that's the point in your map on the finite piece of paper. And go ahead and make a note to yourself, Dr. B, how do I know that that sphere is finite? Well, it's a sphere, right? So the amount of paper that you need is just 4 pi r squared. It's a sphere. It has a radius r. 4 pi times the square of that radius. That's how many square inches. All right, so just get that much paper and then kind of make it into a sphere, and you're good to go. Now, this is a mental exercise. You wouldn't want to do that. Here's another sketch. But one important thing about this is, and this sketch is kind of nice to show this, and it's a good mental exercise to prepare for today's lecture on black holes. And specifically, if you take a point like this one right here, it's going to poke through over here, all right? From this point on the lower left all the way up to the North Pole, kind of pokes through right there. Now, if you take one out here, it's going to poke through at a different longitude and maybe a slightly different latitude, but the North Pole, out to your point, pokes through here. Now, what I want you to think about here is the following. The further away your point is on the plane, so this last one over here on the far right in the middle, it's way out there. Now look where the distant point pokes through. Quite a bit closer to the North Pole. So, the interesting thing is, the further the point is on the plane, the closer the poke-through point, its matching point, is to the North Pole. All right? Now, so the further away on the plane, the closer the corresponding point is on the sphere to the North Pole, right? So stuff that's really close, it'll poke through down here in the southern hemisphere, right? If it's far away, a certain distance away, it'll poke through at the equator, and if it's even further away, it'll poke through the northern hemisphere, and further away, up in the Arctic Circle, and further away, way close up to the North Pole. Question? Further away in relation to the South Pole where it touches. Let me go back to this one. Okay, so further away as measured from, you can't see the South Pole in this diagram, but it's down there. That's where it touches the plane. And this other one, it was bisected by the plane. This is the one that people usually use. This one over here. All right. So the further away your point is, so your surface touches the South Pole, and then just go out a distance, and you can see this one's up. The poke through point here, Z on this one, is up in the northern hemisphere. All right. Now, second point. Infinity itself will be mapped to precisely the North Pole itself. All right, so spatial infinity in any direction gets mapped out precisely to the North Pole. That's the limit. And the limit of large distance. So these rings down here, it looks kind of like a spider web, but these rings down here on the plane, the further out you go, the closer your poke-through point comes to the North Pole. And so the limit of that is the North Pole itself when you get to larger and larger distances going to infinity. So here are these poke-through points, and they get closer and closer to the North Pole as you go. Now, let's get back to black holes, and let's talk about this idea of lensing, gravitational lensing. Now, if you wear eyeglasses or contacts, you know that the lenses bend light rays so that they focus on the retina of your eye if they're properly prescribed, properly ground. Same thing with a telescope. And that is a property of the glass and the shape of the glass. You do the right shape lens, you get it focused where you want. And but that is not what we're talking about here. That is a refraction. Let me spell that for you. refraction. So glass will refract, and you can make a lens. A prism. It's not really a lens, but it refracts light. It disperses light. And if you make a piece of glass a little bit different shape, it'll focus pretty nicely. Okay, but that's not what we've got. We've got gravitational lensing. Now, we talked about this idea that, you could have an actual position and an apparent position. And that during a solar eclipse, you can see something that's behind the star, like this one up on top. You shouldn't be able to see it. But because the light, it kind of cuts the corner around here, over here, grazing by the sun, it just budges around it. It kind of takes a very gentle left turn, and then you can't see it. And so the apparent position is way out here, right? So its true position is here, and gravitational lensing inches it slightly away from that, slightly outward. Now, same thing over here, this second star towards the middle, yeah, you're getting a little bit of inching away, but not as much. Why is that? Because the place where it interacts with the sun and the curvature, and the sun's curvature is not very strong, and this diagram is really exaggerated even so. But you're going to get a little bit of curvature effects here. You'll get a little bit of deflection, but not a whole lot. And then out here, it's you're so far away from the curvature, the intense curvature of the sun, that you don't pick up any deflection at all. Question?
Does gravitational lensing only occur for stars?
Gravitational lensing, does it only occur for stars? No, it occurs for other stuff, and I'm going to show you a couple images. But let me get you this image. Here's another image that I stole from the internet. I do a lot of stealing from the internet, usually from NASA for this class. And I make a lot of my own diagrams. But anyways, so if you've ever been to the mall and seen one of those little games where you put a quarter in it and it spins around, and it's like a funnel-shaped thing, only it's not a cone-shaped funnel like in the kitchen. It kind of curves in and gets steeper and steeper, and the quarter spins, it circles the center, and eventually works down and gets faster and faster. And by the time it's about to go through the hole and you make your donation, it's going really, really fast, and then boop, it falls out through into the collection unit. All right, so that's kind of like this. The presence of mass bends the fabric of space-time. That's another way to think about it. All right, and here's the bending. All right, for you guys in the back, the graph paper here it looks pretty normal. You know, squares up here. But down here, close to this mass of the sun, there's a lot of curvature. The graph paper now looks a little bit more curvy and almost diamondish down here. And so the story is that the photon will catch that curvature if it's close enough. Okay? And so your apparent position will be out here. So this is another picture, and this shows that this gives you a visual image of space-time curvature. Now, space-time curvature is in 4 dimensions, and this is just in 3. But it helps you think about it. All right, and here's another overhead look. This one's nice. Here's the sun here. Here's us on Earth looking at it. And I love this one because this is where the actual star is. And yeah, it's right behind the sun. We shouldn't be able to see it. But if we can get rid of the glare during the total eclipse, and we might actually be able to see it, and we'll see it over here. That'll be the apparent position, all right? Because it gets deflected here. So it's coming in here, and you know, this is the direction where it's coming in, this first blue arrow. And normally, you're not going to see that photon. A photon that comes along that ray of light, no, you're not going to see it. I mean, if you're right here, that's going to overshoot the Earth. It's going to go zip past the Earth. But because of curvature right here, it's not going to zip by the Earth. It's going to look like it's coming in from this direction, the yellow dashed arrow. And so that looks like the place where it's coming from. And therefore, we think, all right, it's budged outward from where it actually is. It appears to be out there a little bit to the right from this perspective. Now, here's another look at gravitational lensing. Now, I want to emphasize that this is for light that's cruising past the sun, cruising past the central object. When we're studying photons, behavior at a black hole event horizon, we're going to be thinking about photons that are going straight out from the black hole, not cruising past. All right, so now these ones, we have the star's actual position here, the blue rectangle, and then the tip of the arrow shows you where the star is actually. And for stars that are in close enough, they'll get a little bit more lensing than, like this one down here. This one gets a little bit, but it's far enough out that you get a little bit of lensing, but not a whole lot. All right? Now, we can see this. We can see, now that we know what to look for. 100 years ago, when Einstein developed this theory, nobody knew if this would actually work or if this was actually occurring. But they observed it in the year 1919, total eclipse, and they knew that Einstein was right. Now, another thing, and this is going to lead us into what happens with other objects besides stars. If you have something behind the sun or behind the central object, you shouldn't be able to see it. A lot of times it'll be revealed and distorted. Oops, let me go back to that. All right, here it is. All right. So that object, it might, if it's an extended object like a galaxy, it can be moved into a position where you can see it by deflection of starlight. But if it's an extended object, it'll look like it won't look like a spiral galaxy. It'll look something like this. All right. So here's lensing of galaxies, Jacob, by galaxies. Okay. Now look at this thing right down here. See this one? This is from the Hubble Space Telescope. You know, they went looking for gravitational lensing events, and then the last 20 years, we've been really cleaning house. We've been getting a lot of them. Matter of fact, they have computers now that automatically look for gravitational lensing. Here's a close-up. See that horseshoe-shaped thing? Yeah. You know what that is? That's a galaxy behind the central. See this thing right here in the center? That's a galaxy kind of close to us. And behind it is another galaxy that we can't see, or I should say we normally should not be able to see. It's a little bit offline, but it forms almost a perfect circle. And you know, when you look at Hubble Space Telescope pictures, if you're looking into the deep field, you find a little break between all the stars in our galaxy, and you look out into the galactic space like this. Every image on this page is a galaxy, by the way. You can see this. Okay, so that thing right there, that horseshoe-shaped, that's actually a galaxy that we would not see if it were not for gravitational lensing by this baby. All right? That's the lens. That's not refraction. It's not a property of glass. Different types of glass have slightly different refraction properties. But this is not anything to do with this. This is gravitational. Right? Sometimes we don't see a smear. Like actually, this is another Hubble Space Telescope image here. You see this arc here? We see zillions of arcs. We see a lot of these, but sometimes we just see a little. It doesn't really arc out. But we see it. It's so far away, and it's so dim that we don't really catch much arcing. That's all right. But we know, what this image is? This is the same galaxy. This one up here and this one down here. You know how they know that? They compared the spectra. It's the same. That's one galaxy, and it's been lensed by a couple of the galaxies in the middle here. And this is a big cluster of galaxies. And this is another one. Everything that you see in this image is a galaxy. You look deep enough, you look between all the stars, or you look perpendicular to the plane of the Milky Way galaxy, and you can see, you don't see any stars in our galaxy if you look through narrow windows and stuff, but you see millions of these galaxies. Millions. I don't know if anybody's counted them all. Here's the basic layout. You could probably make a sketch of this. The idea is, again, for these, Jacob, for galaxies, you've got some kind of a source. All right, this is the thing whose light is lensed. And then in between us, now we're over here in this big frame on the lower right. All right, that's us in this, looking through the Hubble Space Telescope or something. All right, but between us and the distant source is this set of intermediate distance galaxies. And they're the ones that will lens things. Now, if you just have one big one, one big galaxy, and if it's just in the right position, you might get a circle or an arc or a horseshoe. But sometimes you just get another dot, like here, and these two orange dots here. All right? And the nice thing about it is, if we study these carefully and measure them and stuff, try to measure the redshifts and the angular positions and so forth, we can sometimes figure out the mass of a galaxy itself, other than by using Kepler's third law. Now, Kepler's third law is good for binary star systems. Can you do this? Good. We'll get that ejected, and we'll get it ready for this review. Thank you for doing that. So here's us down here. So this is a basic layout, and this is an image I stole from the Hubble Space Telescope Science Institute, which is kind of a cool place. You know, Hubble's that is a great machine up there. We got a lot of great machines, not just Hubble. All right, so let's get back to this idea. That's the third lensing, and this one is a little different, as I mentioned. We've already talked about it, trapping photons at the event horizon of a black hole. These are photons they're not skimming past the sun or the black hole. They're radiating straight out, like the quills of a porcupine, instead of like streamlines going past. You know, the gravitational lensing of galaxies, that's light rays streaming past like streamlines. These ones, here's your outgoing pulse. You know, you light your flash bulbs off for a nanosecond. Though that pulse of light, that wave of light it's heading in the right direction, but because of lensing, they do not diverge. All right, so they're trying to go out along this path, but they don't really get much of a chance because instead of diverging, they're just, you can't really say that they're hovering. They're just, they're just being lensed. And so that gives rise to the definition. This is the definition of a black hole, or of the event horizon of a black hole. The outermost surface of trapped photons, trapped by this intense curvature, or trapped, as you might say, Asia, by gravitational lensing. Right? Now, if you have some light bulbs further out, that's good. You know, they'll be able to stream outwards. They'll still be affected. They'll be redshifted. But yeah, if you're a little bit further out than the event horizon, you can do it. You know, and you can aim stuff in as well. But it's the outgoing photons that are the most interesting ones. And at this stage, if they're aimed outwards but don't diverge, instead they converge by gravitational lensing, curvature, that's your, and if it's the outermost surface, that's the event horizon. Now, I want to go through some of the spherical coordinates around a black hole. So let's just review spherical coordinates for a minute. The simplest black hole is spherically symmetric. All right? We can study electromagnetically charged black holes. We can study spinning black holes. And those two effects change things. But if you just have a spherically symmetric one, to locate an object, you're trying to journey into a black hole, you want to know the latitude and longitude of your position, and you want to know how far you are away from the center. All right? Now, this is similar to a globe of the Earth. A globe of the Earth, to locate a country or a city, you need its latitude and longitude. If you look on Google Maps, you type in a latitude and a longitude, you'll get the city that you want. Or if you look up a city in Wikipedia, they always have the coordinates of like the center of the city. All right, I do that all the time. All right, but we don't, in Google Maps, in a globe of the Earth, we don't really worry too much about the radial distance, number 3 here, simply because from the top of Mount Everest to the bottom of the Mariana Trench is just a few kilometers. It's not that many kilometers. All right? So the radial distance for everything on the globe is about the same, plus or minus a few kilometers. Because the radius of the globe is about 6,400 kilometers. So, throwing in a plus or minus of 10 kilometers, it's not that much. All right? Anyways, the traditional name for a spherically symmetric black hole is Schwarzschild. Schwarzschild. It's one of those German names, kind of like Brickner, infinitely misspellable, infinitely mispronounceable. If you don't want to do either of those, just say, oh, spherically symmetric black hole. Okay, Schwarzschild is the guy that figured it out back in about, I think it was I want to say it was 1915. Very soon after Einstein published his theory, this guy figured out, whoa, this geometry is going to have something exotic. It's going to have a black hole. Okay, so let's go and talk about some of the special spherical radius positions in and around a black hole. Now, the radius of the event horizon has a special name. It's called the Schwarzschild radius. The formula for it, by doing a bunch of really fancy calculus and trig and stuff like that, and you like 4 or 5 pages of algebra, the formula for the radius r of the event horizon is 2 times capital G, Newton's constant, the gravitational constant, and then capital M, the mass of the black hole. So that's how many kilograms in the iron core of, your core collapse. And then divided by c squared, the square of the speed of light. Right? Now, if you do this, for instance, if you make this calculation for the Sagittarius A star, about 4 million times the mass of the sun, you get a pretty big Schwarzschild radius, right? It's measured in astronomical units. If you make, if you take something that's 5 or 10 times the mass of the sun, you get a much smaller one. The sun itself, if we could cram the sun down into the sphere of approximately, a few kilometers, then we could turn the sun into a black hole. But we don't know of any physical process where that ever is going to happen. So we don't think the sun will ever become a black hole. Pretty much mostly it's going to become a white dwarf, we think. But if we could get it down to a kilometer or so, yeah, the sun would be a black hole. But the thing is, everybody's always, oh man, black hole, I'm going to get sucked into it and stuff like, I'm doomed. No. If you replaced our sun with a black hole of the same mass at the location of the SUN, we'd just orbit, just happy as, we'd freeze to death. We wouldn't be getting any sunlight, we'd die pretty quickly. But our planet would just keep cooking along there, So Mercury might get greased. But. Now, astronomers and physicists in general, scientists in general are kind of lazy. So our astrophysics shorthand for the Schwarzschild radius is just r equals 2m. So it's kind of like, when you're spelling in first grade and you first learn about silent E, like in the word, no, not the word shirt. There's no E in the word shirt. Sure? Yeah, okay, sure, S-U-R-E. I was thinking fine, F-I-N-E. Phone. iPhone. I didn't learn about that in first grade. Anyways, phone, P-H-O-N-E. And so we just make the capital G and the C silent, just because we're slackers. Now, there's another interesting location in the geometric configuration of a black hole. It's at r equals 3m, so another 50% further out than the event horizon. And it's called the photon orbit. And at this particular orbit, if you have a photon that is streaming past the black hole, it will fall into a perfect circular orbit. So if you're at that distance, 3m, and you fire a laser beam, not into the sun, but perpendicular to that, so it's just grazing past the black hole, it'll go into a perfectly circular orbit. But if you're a little bit off, if you're just like a millisecond of arc off, it'll take some laps, but eventually it'll go in. Or it'll take some laps and then eventually go away from the black hole. So it's not a stable orbit, but it's a theoretical orbit that is sometimes interesting to study. Another place of immense importance is the very center, r equals 0. This is what we call the space-time singularity. And this is like a hole punched out of graph paper, but it's a hole punched out of space-time. So you can't, if you have a piece of graph paper and you punch a hole in it, and then you say, okay, I'm going to draw with my pencil from point A to point B, and I cannot leave the paper. If there's a hole in the graph paper, you can't cross it. All right? You can't get to point A from point A to point B through that hole punch in the graph paper. The same thing here. All right? It's a location where all the iron in a core collapse supernova, that's where it ends up. And it ends up in a region of 0 volume. And you may think to yourself, Dr. B, what in the world are you talking about? How can all those iron nuclei get squished down into an r equals 0, 0 volume? What is that? And yeah, join the club, because nobody knows, you laugh, but I mean, we struggle. A lot of guys try to figure out, well, what happens to all that material? I mean, we know that it goes down to r equals 0, but how do you describe the physics of something that is 0 volume, infinite density? It's just, so that's why we call it a singularity. It's a place where we don't know any physical laws. Kepler's third law, not down there, baby. There may be some law, but we don't know what it is. We're trying to figure it out. There's all kinds of exotic theories. And then the fourth place, the fourth locational type area, is just the limit of infinite distance. So just like in a couple images ago, we looked at that blue graph paper, and it kind of had the curvaceous area and then the flat area where the graph paper lines were, good and rectangular, and the curvaceous area where they weren't. As you get farther and farther away, so the limit of distance beyond bound, space-time flattens out, so you don't have any curvature effects. Right? And that's where we are for the most part. The sun is the nearest place where we can see any kind of curvature. Actually, I take that back. We can measure the curvature of the Earth, or the space-time curvature due to the mass of the Earth, but it's really weak. There's ways to do it with lasers and stuff. Question?
Like, for black holes, how can you categorize a black hole if it has no volume? Like,
Yeah.
how do you categorize it? Like,
Yeah, I'd like to know. No, how do you categorize a black hole if it doesn't have a volume? And actually, what we say though, Desiree, we say that the black hole has a volume, the volume of the event horizon. Okay, so we do know that, and it has a mass, but we just don't know where the mass is. It's like a remnant, it's like space doesn't have any matter, but it still has the signature of so many kilograms of mass. And it's, if it befuddles you, join the club. It befuddles all of us. We just, all the math works out, and a lot of the observations work out. So we're pretty sure it's true, but it's hard to understand. Jacob.
If you shoot a laser of light into the photon orbit, but you skew it a little bit so that it'll eventually shoot back out, will it come out faster?
No. Light always travels at the same speed, so if you shoot a photon a little bit askew from the photon orbit, it'll take some laps around, but it'll eventually head out to some distant star. Or it'll spiral in, into the event horizon and stuff. And there's all kinds of calculations, but you would need to go 2 or 3 years of grad school, and then only if you're really brave would you take a course in relativity before you can make the calculations. Now, I did some calculations last night in preparation for this. We're going to now look at light cones near a black hole, and especially near the event horizon, r equals 2m. And the black hole that we're going to look at is the one that we started talking about at the beginning of the semester, Sagittarius A star. Go ahead and make a note. Sagittarius A star, the mass is about 4 million times the mass of the sun. Now, I made some calculations with that last night, and that's what we're going to talk about right now. So what we're going to try to figure out is, okay, here's a couple of my locations, 2m and 3m. Here's my black hole over here, and notice that and r equals 0 is the very far left edge, all right? And then 2m, and then try to eyeball in 3m in the right proportion. And then I've got a little zigzag here to indicate a break in the axis, and this is going to be r going to infinity, where space-time is flat. We'll talk about what happens out there. And we're going to talk about the black holes as they get closer and closer to the event horizon. Now, over here in green, for those of you that are fans of the photon orbit, yeah, that's in green, okay? And then the black hole is a black circular disk, or half a black circular disk, in the middle on the left. Right, now, this is the black hole, the center of our galaxy, about 4 million times the mass of the sun. And what we're going to do is get you in a mothership, and then you're going to bail out of your mothership at this distance, 10m, okay? And you're going to be armed with a blue laser like you could buy at the store, and you're going to be flashing signals back to the mothership and back to Earth. All right, question?
What happens to photons between 2m and 3m?
A photon between 2m and 3m? It depends on how it's aimed. If it's larger, if it's shown out from a laser or something, a little bit out from 2m, eventually it'll go off to some distant star. All right? If it's at 3m exactly and the right direction, it'll circle infinite, till the cows come home. All right? But in between there, but if it's just dipped a little bit inward, it'll spiral in and across the event horizon, and you can calculate all that stuff. You can calculate, well, it'll make 37,293,106 loops, and then it'll cross the event horizon. Whatever, it depends on all the size of your black hole and stuff, but you can calculate. It's not easy, bud. So here's our setup, all right? So your mothership is going to be here at 10m, and here's what you're going to do. You're going to climb out of the airlock, okay, in your spacesuit. You're going to hold on to the spaceship, and you're going to do a test run with your blue laser. Now, I looked it up on the internet, and you can write this down. A blue laser pointer that you can buy on the internets is 532 nanometer wavelength. So go ahead and write that down. The blue, and I'll just make a blue flash here. It's built on Earth. Here's a blue flash. Okay. 532 nanometers. That's the wavelength. Yeah. 532. All right? And that's the one that we're going to be using. Now the problem with that is it's going to redshift as it moves away from, so if you shine, so you're out there holding onto the spacecraft and you say, all right, I'm going to shine it into my hand and just to test it, and like a sound check. And okay, it looks blue, it shines at your hand, everything's blue. But then, okay, now you shine it towards Earth, towards home base, and by the time it gets to Earth, it's going to be red shifted. Now, it's not going to be red, it's going to be green. It's going to be Doppler shifted into the green. All right? And this one, from 10M out to Earth at infinity, it goes from 532 and it elongates to 594.8 nanometers. All right? So go ahead and make a note of that. If you shine a blue laser, 532 nanometers, from 10M, near our galactic center, our big black hole down there, by the time it gets out here to flat space-time at Earth, it's going to be Doppler shifted into the greens, 594.8 nanometers. That's green. Maybe a little yellowy. All right? Now, let's say you bail out, you let go, and you start sliding down towards the event horizon, okay? But you're brave, you're going to do it. And let's say you get to 5.5 M, all right? And you get to 5.5 M, and at 5.5 M, you flash you send your SOS, or you send your I am okay, in Morse code, whatever message you're sending. By the time it gets back to the mothership at 10M, guess what? It's redshifted just about to the H alpha. H alpha is 656 nanometers. This one, from 5.5 M out to 10M, a blue 532 nanometer laser will redshift to 660 nanometers. So pretty close, just a little bit deeper than H alpha. And this is what I was trying to do last night. I was running all my numbers. So these numbers are righteous. Question?
I'm just curious why it's red shifting when it's going towards the observer. When something's going towards you, doesn't it blue shift?
It's the curvature of space-time. Yeah, you're right. I mean, if you're moving, but the thing is, you're also falling into the black hole. But this is a gravitational redshift. It's not the redshift of motion per se that we have. Now here in flat space-time, we can measure that, and cops do it all the time, right? But that's not what this is. This is just purely gravitational. Okay. Now, question. What? I can't really hear you.
What we need to remember from this? Like what you're teaching us, what we need to remember, what would you know the test?
Oh, I'm not really teaching you anything. If you don't want to remember any of this, you don't have to. But the point here is that we're redshifting. And I'm giving you the exact redshift. This guy, you blaze out your laser at 5.5. By the time that flash gets to your mothership, it's redshifted to 660. By the time it gets back home to Earth, it's even further into the reds, 667. All right? So the topic here is gravitational redshift, just like I was telling Kayla. Now, here's what you want to remember. Remember I told you last time that two different ways to think about a black hole. In other words, what the photons do and the geometry of space-time, and also information. Think about this. If you have a good internet service provider, you have a lot of bandwidth, all right? You can send a lot of megabytes per second if you have a big bandwidth. That means you have a high frequency signal, all right? The more frequency you have, the more information you can jam into the channel. Now, when something gets redshifted, you're losing bandwidth, my friend. The gravitational curvature is stealing bandwidth. So the problem here is you're trying to send ones and zeros back home to Earth, and you're losing the ability to do it efficiently. There's only so much information you can send. So gravitational redshift and also information loss. All right, so just put down etc. All these redshifts, you can work them out. Eventually it'll be redshifted down into the infrared. I figured out where that is. That's pretty close to the event horizon. This is the last one I'm going to do. I'm not even going to go down to 3M because it's shifted way down into the infrared. All right? So now I want to go through a couple other things here because, like I was just saying, when you lose bandwidth, that means you can't download stuff fast. You can't upload stuff fast. All right? And so what happens here is you might have this conception that, time slows down. No. Time doesn't slow down. You've got, you bail out of that spaceship, you got a Timex bolted or wrapped around your wrist. You got a blue pointer. The blue pointer is always blazing out blue. Your Timex is clicking along, just like your heartbeat. No problem there. But what the disagreement with the laser is the color. Somebody on Earth is going to measure a redshifted version. You're going to always see it as blue. By the time it gets to Earth, they're seeing it as red or maybe even infrared, radio waves. Okay? So, and you might disagree about time. Slow download, man. No. Time doesn't run more slowly for you jumping out of the spacecraft. What happens is your time measurements with your Timex disagree with our Timex measurements here on Earth. And so here's one way to express that. Our clocks here on Earth will buzz around to infinity before we see the last tick of the astronaut's Timex before he dips into the black hole event horizon. And now that's for us. It's not time slowing down. Our time's still going 60 seconds per minute. That's not a problem. It's just that when we see him dip into the event horizon, our clock's going to be, going to infinity. In other words, we're never going to see him dip into the black hole, into the event horizon. But for him, he sees a finite number of seconds on his Timex. Maybe 37 seconds, or depending on the size of the black hole and how fast he jumps out of it, or he dives into the black hole, how big the black hole is. But he's going to count a finite number of seconds. And that, my wonderful students, is at the heart of the contradictions and the unusual things in relativity. The disagreement between temporal and spatial measurements. Okay, so make a note of that. Right? The photons get redshifted by curvature if they're outgoing. And, from Earth, you'd see his wristwatch and laser continually getting redshifted. And matter of fact, it would shift into the infrared. And then down into the radio. So it shift below infrared into microwave. And then into FM radio wavelengths. And then into AM radio wavelengths. And longer, and you'd be downloading way less and less information as he gets closer and closer. So there's a lot of really unusual things happening here. Now, let's talk about the light cones. Out at our going to infinity, we've got nice 45-degree light cones. Everything's looking copacetic. But as we get in close, for instance at 10 M, the light cones start to tighten up. This is what happens to the light cones. The outgoing radiation is redshifted. The light cones tighten up. Now watch what happens, and I've got this animated. What happens at the event horizon is the following. There it is. It gets wider and it tips over sideways. And that, my wonderful students, go ahead and make a note of that. Light cone tips over sideways. It used to be, the time axis was going like this, perpendicular to the radius axis. Now it's lined up with it. Inside the event horizon, the light cone broadens and flips over sideways. Here's a close-up of it. All right? And here's the time axis. The time axis, if you get your light cone, the time axis goes right up the middle of it. All right. There it is. And guess what? It means that this r equals 0 is the future of everything now. R equals 0 is the future of everything that penetrates the event horizon. And you can see it by the flipping sideways of the light cone. Now, what does that mean to have r equals 0 as the omni-future, the future of everything? Well, let's look at a regular calendar. Regular calendar, preceding time, flat space-time, 1 minute every 60 seconds, 1 day every 24 hours, everything's normal. You go across your calendar, and one of the things about this, you may not have ever thought of it this way, but you can. A specific date, there's something inevitable about the future. So next Tuesday, your final exam, it's inevitable. It's going to come. There's no way to evade it because we're going forward 60 minutes per hour. All right? But spatially, when we walk across and up a stairs, we can walk across the other 3 dimensions. Now, Einstein said there are 4 dimensions. All right? Time is one of them. And this is the normal behavior of time and the spatial dimensions in flat space-time. Now, inside the event horizon, here's what happens. The inevitable event is a location, not a day. So instead of this Tuesday, the 15th, on this mythical calendar here, instead of that being inevitable, the new inevitable point is a location, the center of the black hole. And that is what it means for everything in the event horizon to be squished down to 0 volume. So what it also means is that as opposed to out in flat space-time, regular calendars, where we can walk up and down, left and right, forward and back, inside the black hole, we can now walk the time coordinate. And we can't do it out here. We're always moving forward. We can't go back and forth. We can't go backwards in time. But inside there, we can walk it. And so the calendar has become a chessboard. And we can make moves on it. And so the fundamental lesson for you to remember for the final is this. At the event horizon, the role of space and time changes. They flip. And now, instead of a regular calendar, you have a chessboard. And the inevitable is a location, the very center. Question?
Okay, so if you can't move because the location is inevitable, how exactly would you walk time? What exactly would that look like?
Yeah, I don't know. Nobody knows. Because nobody's been able to get inside of a black hole, and it's certainly nobody's been able to report back, because you can't. But we're trying to think it out. We're now getting to stuff that we don't know the answers yet. All right, now, before we start the in-class review, let me remind you that we have a mega review homework this weekend, and you'll see it probably tomorrow sometime. And you'll have until next Monday night. Use it as a study tool and convert it to bonus points. All right, now it's time for the in-class review. Can you come up and help hand it out? We're going to hand out these things. We've got about 15 minutes. We've got 20 questions. Do your best. Circle your answers. And I'll start the clicker up here. And we'll convert this into bonus points as well. So get these handed out. Just hand them out in bunches. A few for each row. And then just as fast as you can. Because we're running low on time.